Next speaker, Jitao Liu from Federal University of Rio.
Thanks, introducer. Firstly, I would like to thank the organizers to give me this opportunity to speak here. I'm going to talk about on the boundary partial regularity for the incompressible Navier-Stokes equations. And this work is joint with Wendong and Zhou Ping. And first, I want to recall the time-dependent incompressible Navier-Stokes equations and the steady incompressible Navier-Stokes equations as follows. And as we know, global regularity of solutions to the time-dependent Navier-Stokes equations in 3 space dimensions is still a wide open problem. And start from 1976, Schaeffer established various partial regularity results for weak solutions satisfying the so-called local energy equality. And Cabrelli, Cohen, and Nuremberg in 1982 firstly introduced the notion of suitable weak solutions. And they also proved that for any suitable weak solution, U and pi, there is an open subset where the velocity field U is regular. And they showed that the 1D Hausdorff measure of the complement of this subset is equal to 0. And I have to mention here is the difference between weak solutions and suitable weak solutions lies on the latter notion requires a generalized energy equality and an estimate for the pressure. And the key idea in our seeking is to establish certain epsilon regularity criteria, which have many other important applications. The first one is Sergey and Surik use this idea to prove the regularity of L3 infinity solutions to the 3D Navier-Stokes equations. And the second one is they were used by Jia and Surik to construct forward self-similar solutions from arbitrary -1 homogeneous initial data. And some simplified proofs and improvements can be found in many other works. And notice that time corresponds to 2 space dimensions. Zhu in 1988 proved the following interior regularity results. And it is also mentioned in Zhu's paper that it would be interesting to know if analogous partial regularity results holds in dimensions n larger than 5. And Dong and Strun in 2012 use a bootstrap argument to prove the interior regularity in the 6-dimensional steady case. And a question is, what about the boundary partial regularity? And it is started from 1982 by Schaeffer to study this problem. And the second partial regularity results was also extended to the flat boundary and C2 boundary by Sergey and their collaborators. And in 5-dimension stationary case, and Kang in 2006 proved the boundary irregularities. And there is natural question, can we get the boundary partial regularity of 6-dimensional state case? And the answer is yes. And we should notice that the previous arguments by Sergey or Kang based on the compact arguments can't work here. So motivated by the bootstrap argument due to Dong and Strun, we use an alternative proof to prove the following theorem it is with directly boundary condition. And the difficulties lies on the control of the pressure associated with U. And for the interior case, the pressure can be decomposed as a sum of harmonic function and a term which can be easily controlled in terms of U by Cardinal-Riemann estimate. And for the boundary case, there are slow decaying terms, this one, and this one. They have the same order. So this seems impossible to obtain an effective iteration scheme by their methods. So let us take some time to review the proof. We call the local energy inequality and scale invariant quantities like this. And to overcome these difficulties, we first derive a revised local energy equality. For interior case, they choose this test function, and for boundary case, we choose this test function, and we plus a free parameter k. And this give me a lot of help. And by this parameter, we can get revered local energy inequality. And this parameter can control the function of every terms of this inequality. And use this inequality we obtain. And by take k large enough, we can find a new quantity such as the following uniform estimates holds, like this. And then this can lead to an effective iteration scheme. And I have to say now, thank you for attention.